So today we'll be briefly talking about even and odd functions. So in this course, when we were dealing with polynomials, we talked about an even degree polynomial and an odd degree polynomial. Even and odd functions are a completely separate thing. Okay, there is some relationship, but they're completely different definitions. So when we say that something is an odd function, what that means is that f at negative x equals negative f at x. That is what we call the algebraic definition of something being odd. So in other words, if for instance we found what f at negative 4 is, then that's going to equal negative f at positive 4. Now, this is the algebraic definition, and in this class we really won't be dealing with that just due to time. We're going to focus on how to recognize even and odd functions graphically. But if it was day school, then we would have spent some time going through the algebraic definition of even and odd functions. So, how do we do it graphically? Well, odd functions are symmetric about the origin. And what that really means is it means that they have rotational symmetry. About the origin. So what rotational symmetry about the origin means is it means that if we fixed the origin and kept it centered and we rotated the graph 180 degrees, we should end up with the exact same graph. So I'm going to outline my graph here for a minute. And if I do a good job, this will hopefully work. Okay, there it is. So if I take this graph and if I rotate it 180 degrees, we end up with the exact same graph. That means that it is an odd function. Okay, 180 degrees, we're back. So if you can flip your graph essentially upside down, then it is an odd function. And it is important that you have to flip it around the origin. Okay, so rotate it 180 degrees, essentially turning your paper upside down. You would have an odd graph, an odd function, if the graph stayed the same. For even functions, then it's true that f at negative x equals f at x. So what that would mean is that if we put in f at negative 4, it's going to give you the exact same value as f at positive 4. So that's its algebraic definition. In terms of the graph, even functions are symmetric about the y-axis. So it has what we call line symmetry. And it's line symmetry about the y-axis. So what that means is that we can fold our graph along the y-axis and we'll have the exact same thing on both sides. Okay? Or you could flip your entire graph across the y-axis and you would have the exact same thing. So once again, if it's an odd function, it has that rotational symmetry. Rotate your graph 180 degrees around the origin. If it's an even function, it has that line symmetry. You can essentially fold your graph in half along the y-axis. What about if it doesn't have either of these properties? Well, if it doesn't have either of those two properties, like most graphs don't, then we say that it is neither even nor odd. Okay? And that's all we're really going to need to know for this course. So let's do a few examples. So here's our first one. We want to determine whether each of these functions is even, odd, or neither, and we're not going to bother verifying algebraically. So here's our graph. So you have to ask yourself, if I rotate it 180 degrees, does it get me back the same graph? And in this case, if you flipped it upside down, you would in fact get back the same graph. So that means that this is an odd function. And it's an odd function because it has that rotational symmetry. So here's our next one. So if you look at this one, if you rotate it 180 degrees, you don't get back the same graph. You would have an upside down M shape. But if you fold it along that y-axis, all the points do match up. So it does have line symmetry. And if it has line symmetry, that means it is an even function. Okay, here's the next one. If you rotate it 180 degrees, it would give you back a similar graph, but it won't actually match up perfectly. And the reason it won't match up perfectly is that on this side, the x-intercept is at 3, but here the x-intercept is at -4. And if you were to rotate this around, those two values would switch. So it doesn't have rotational symmetry. If you tried to fold it, they definitely don't match up. So it doesn't have line symmetry. So it is neither even nor odd. Here's our next one. It's a sine graph, because you can look at even and odd functions without it being a polynomial. You can actually do this for any type of function. So if we look at the sine graph, and if we were to flip it 180 degrees about the origin, you would actually get back the exact same graph. So that means that this is an odd function. And using that algebraic definition a little off to the side, remember that whole f at -x equals -f at x thing? If we replaced f at x with sine, that tells us that sine of -x equals -sine of x. And you'll see in some places that's actually an identity, and the identity comes from the fact that sine is an odd function. So you don't need to know that, but a little interesting connection between even and odd and identities. Here's the last one. So cosine goes on forever. If you fold it on the y-axis, you'll see that all the points do match up. So that means that cosine is an even function. And once again, using that algebraic definition, that tells us that f at -x equals f at x. We also know that cos of -x equals cos of x. And that is another identity that you will sometimes see. So the important thing to take away here is that you need to be able to recognize even functions, odd functions, and neither, and for us, just based on the graph. Okay, so you're looking for that rotational symmetry about the origin or the line symmetry about the y-axis.